Okay, well, this should be interesting. Okay, well, we're at the end. We've made it to the last day. Congratulations and thanks for coming. So what are we doing today? We're going to do some more review problems from the practice problem set. And hopefully we should finish up because, after all, there's not another day. But there will be more review sessions, and I would encourage you to come to at least one. I'm doing one on Sunday from 1 to 3, and that will be, I'll go over the practice finals. And so I'll talk about them. And not just like, here's a solution, I'll talk about sort of like, what should you be looking for? What should be going through your mind as you see these problems? How should you approach them? So that will help. And as an added incentive, what I've done is I made a one sheet that has everything that you'll need to know for the final on one piece of paper. And you can pick one up at the review session. There'll be another one that Renee, who's the SI person, will give you Sunday evening, 5 to 7 if you like. And if you like to wait till the very last minute, and some people do, there will be one Wednesday, which is the night before the exam, from 7 to 9 in this very room. So yay! Okay. All right. Anything before we get going? Yes?
Who's gonna give us the review session on Wednesday?
And where?
Who's gonna give us the review?
Ah, this one on Wednesday. The person giving the review session on Wednesday is Dr. Elgin Johnston, who has been teaching for many, many years. He's a very well respected and highly awarded professor. And he has a different style than I do. And it's good to see people with different styles. That's who will be giving the one on Wednesday. Anything else? All right. Good. Well, let's run through it. Today is integration. So you should know a couple of basic properties of integrals. For example, if I integrate from a to a, where a could be anything, a could be 5 or 3, usually that tends to be 0 or 1, then no matter what I'm integrating, I get 0. It's a freebie. It's a nice, easy integral to do. If I switch the order of integration, I'll change the sign. So the integral from a to b of the function f of x dx is the negative of the integral from b to a of f of x dx. I can also combine regions. So going from a to b and then from b to c is the same as going from a to c. And that's regardless of what order a, b, and c have to each other. So don't worry, it's like, oh, a has to come before b and b has to come before c. That is totally irrelevant to this fact, which is beautiful. If you have an odd function and you're integrating from negative a to a of an odd function, you get cancellation. So if you think about it in terms of area, you get some positive area, negative area, canceling out. And this last integral statement down here at the bottom basically says, look, integrals are nice. You can pull them apart. And you can also pull out constants. And so the idea of being able to pull integrals apart is very convenient. In fact, it's a very useful tool. So if you ever encounter an integral and say, these different pieces don't seem to really work really well, but maybe if I separate them and do each one individually, then I can do it, and it's not so bad. So that's an important idea from this last part down at the bottom. Okay, so let's do an example. Suppose we ask you for the following: the integral from negative 5 to 5 of 3 plus t to the 7th cosine t. What can we do? We can certainly separate. So that we can say, well, look, whenever I see a plus in the middle, I can say this is negative 5 to 5 of 3 plus negative 5 to 5 of t to the 7th cosine t. Now, hopefully, separation was useful. Does it help us on one of these two integrals? Well, hopefully it helps us on both of them, but I claim that one of these integrals is easy, and the other one is also easy. So which one is easy? The first one's easy. You can integrate that. In fact, you don't even have to do any antiderivative. It's just a constant 3. And you're going from negative 5 to 5. That's the length 10. So if you think about this geometrically, that's a 10 by 3 rectangle. What's the area? Or what does this integral become? It's 30. Now, somehow I said that this was easy. Why is that easy? It's an odd function. T to the 7th cosine t is odd. The integral of an odd function over negative a to a is 0. Okay, so you have 30 and 0. They combine to give you 30. And that's the answer. Okay, so another example, because working with integration is very important. It's probably about half the test. Write the following as single integral. I probably should have put the word as a single integral, but this is not an English class, so. All right, integral from 1 to 6, plus the integral from 1 to 4, plus 2 times the integral from 1 to 2, plus the integral from 6 to 4. Well, what are things we can start seeing right away? One thing I can see right away is that if I compare these two, notice that the top bound on the first one matches the lower bound on the second one. So that fits into this criterion over on the left. The integral from a to b plus the integral from b to c is the integral from a to c. So I can combine those two to 1 to 4. Oh my goodness, I forgot a dt there. Ah, there's typos everywhere. But not on the final. That's been thoroughly scrubbed. It's a beautiful test. Most beautiful test I've ever written. I spent hours making one of the pictures. You'll know it when you see it. You'll be like, oh, that's a beautiful picture. That must be the one he spent hours making. Now, what can we do with these first two? Yeah, they're the same thing. So it's just 2 times. Okay, so 2 times the integral from 1 to 4, f of t dt, plus 2 times the integral from 2 to 1 of f of t dt. Now that there's both the 2 times, now the last thing is to say, well, let's think about this. 2 to 1, 1 to 4. So again, we're back into the case where the bounds are matching. So I can apply this a second time. So I'm going to have 2 integral from where to where? 2 to 4. And that's the answer. All right. Now the next idea is, I already appealed to it slightly there, and that's the following. You can use geometry to do integration. So oftentimes people think, oh, integration, the only thing that you do to do integration is you find an antiderivative and then that's it. That's the only way we can do integration. But there's other ways we can do integration. We've seen a few examples of this where we saw crazy, bizarre functions, cosine x to the sine x over dot, dot, dot. There's no way you can find antiderivatives, but you can still find a value. We're going to see a really cool example either in Calc 2 or, excuse me, or Calc 3, where you can't find an antiderivative, but you can still find values. So don't think that, oh, if I see an integration, I must find an antiderivative, and that's the only option I have. What you should do is say, here's an integration. How should I be thinking of it? One way to think of it is, well, maybe there's an easy antiderivative. But another way to see it is, I wonder if I can interpret this in an interesting way. And one of the ways we've learned to interpret integrals is as areas. Maybe I can interpret an integral as an area. Now, for geometry, when I talk about using geometry, things like rectangles and triangles and circles, oh my. But we put them together. We say, well, what do we get? So here's an example. Find the integral of the square root of 1 minus x squared minus 2 absolute value x minus 2. Now, if you see this in Calc 2, you'll probably start saying, oh, I know how to integrate square root of 1 minus x squared. You can do some crazy trig substitution stuff, and half an hour later, I'll get the answer out. But the good news is we don't know enough yet. And that's good news because it's like, okay, we're not going to go into a complicated root. Let's go to a simpler root. All right. I can interpret this. I can interpret this as one curve subtracting from another curve. So it's really like I'm finding an area between two curves. The top curve, square root of 1 minus x squared, what does that become? It's a circle. Yeah, this is our classic circle. Circle of radius 1. 2 absolute value x minus 2. That's the lower curve. Well, what would that look like? You know, imagine that Iowa State had been able to successfully score a touchdown this semester. What would you be doing with your arms? You'd be doing this. Now, you're probably not used to that because, you know, we didn't have a good football team this year. But 2 absolute value of x minus 2 is a v. Now, the 2 makes it skinnier, and the minus 2 shifts it down. So what it looks like is it looks like a shape that does this. So this is at negative 2. So I've moved the tip of the v down 2, then I've made it somewhat stronger, stretched out. Okay, this is at negative 1, this is at 1. And so I'm looking for that. I say, okay, well, that's not so bad, because I can think of this as 2 pieces. What's the top piece? What in terms of the area? It's half the area of the circle. How much area is in a circle of radius 1? Because this is a circle with radius 1. Pi. So it's half pi. Now, I can also say then the other piece is this part down here. Well, it's a triangle. Base 2. Height 2. What's the total area? 2. Lots of 2's. And so therefore, the integral is half pi plus 2. And we're done. So one of the fun things that we get to do in Calc 3 is try to find ways to ask you to do integration without actually doing integration. This is good. I like these kinds of things. Okay. That's using geometry. Let's get into things, because I'll have to be honest, geometry is fairly limited. To be able to use geometry, we have to have a few shapes that we're familiar with, and there's not that many shapes available to us that we're familiar with. So, okay, suppose we don't have geometry. Can we at least approximate the answer? And so this is the only time that you'll see approximation with integration. So I should say there's 2 times you'll see approximation. One is when we talk about linearization, and that's approximation related to differentiation. And the other one is with Riemann sums, and this is approximation with respect to integration. And the idea here is that I'm taking my curve, so I have my curve and between A and B, and I'm breaking it up into pieces. Now when I say it, I should be careful here, because there's lots of things it could be. I'm breaking my interval between A to B up into several pieces. And I want to know the total. Well, what I can do is I can say, well, what's the total on each part? Integration is not about area. I know that we oftentimes talk about integration as area. Integration is one interpretation. Sorry, area is one interpretation of integration, but it's not the only one. Integration is all about finding the total. How much is there? And so one of the things we can do is we can say, well, how much is in one of these little pieces? We can approximate each piece. And the way we do it is we pick a point. So for instance, we might pick the left point. And we get these series of rectangles based off of the left point. And the key observation here is that these rectangles are not perfect. They don't exactly match the function, but they're pretty close. And so it gives us a reasonable approximation. And of course, we can make better approximations by making more rectangles. And so we have the following, that the total is the sum over the parts. That's what we mean when you see a capital sigma of the contribution from each part. And the contribution from each part is a combination of the function evaluated at some point, usually left, right, or center of the interval, times the width of the interval. Okay. So, for Riemann sums, the key is it's a summation. Figure out where you're doing your evaluation. Figure out your widths, write down your sums. So here's an example. Suppose we want to approximate the area under y equals x squared minus 3x plus 5 between x equals 0 and x equals 4 using Riemann sums. And we need to specify some things. We need to say how many intervals. So this one says 4. We're going to break it into 4 parts. And we need to specify, well, what endpoints do we want to use? Okay, this says right endpoints. Choose the right. So here's what we're going to do. We're going to start by saying, all right, let's think about how we're splitting it up. So I'm going from 0 to 4. I'm splitting into 4 parts. Where will these parts in the middle be? 1, 2, and 3. So whoever wrote this problem wanted us to have nice numbers to work with because they were a very generous test writer. All right. The other thing is we have to pick points. So each interval, so there's 4, 0 to 1, 1 to 2, 2 to 3, 3 to 4. Each one of them we have to pick 1 point. And now we're going to pick the right. So for example, for 0 and 1, which point do we pick? 1. For 1 and 2, which point do we pick? 2. 2 to 3, we pick 3. 3 to 4, we pick 4. So we're always picking the right. So now I can write down my Riemann sum. I can say that the total, in this case, area, is approximately, I go to each interval, the function at 1 times 1 plus the function at 2 times 1 plus the function at 3 times 1 plus the function at 4 times 1. Now, where are these times 1 coming from? They're the widths, the delta I. All right, so we're almost done. What happens when I plug 1? Oh, by the way, what was our function? Our function was this x squared minus 3x plus 5. That's our function. What happens when I plug 1 into that function? What do I get? I get 3. What happens when I plug 2 into that function? I thought that's what we got when we plugged 1 in. Ah, see, we can get it the same thing twice. Yeah, that's cool how that works. Okay, what happens when I plug 3 in? I get 5. And now when I plug in 4? 9. 3 plus 3 plus 5 plus 9, if I put those all together, I get 20. And that's the answer. So Riemann sums are fairly straightforward. Just remember, break things into part, figure out what's happening on each part. All right. Of course, I will say Riemann sums are great in practice, and computers love them, but hard for us to do. Hard for us to do. So the next theorem is an important theorem, and this theorem puts the fun into the calculus. It's the fundamental theorem of calculus. And it says, look, there's this nice relationship between differentiation and integration. In fact, there's 2 nice relationships. So let's talk about what the 2 nice relationships are. So the first one says the following. If you look at the integral from a to x of f of t dt, so the way you think of that is what's the total accumulation that you have for the function little f? So how much have you accumulated between a and x? So as you vary x, that value is changing. So what's happening is that inside that derivative, that's actually a new function. And when we take the derivative of that, we recover the function f. So in essence, what we're saying is that the change, that's the derivative, the change of the total accumulation is the function that we're accumulating. That's the fundamental theorem of calculus. Now the second one says the following. Suppose you have an antiderivative. So this is what this first part says. F prime of x is little f of x. That's saying that this function capital F is an antiderivative of little f. Then the integral from a to b of little f of x dx is capital F of b minus capital F of a. Now, the second part here, this part is what you will see in practice in terms of when you're actually doing the integration, you're going to make an appeal to use that fact. The first part is what you might see more directly on a problem. So we very rarely test you on this fact. It's sort of implicit in what we do with definite integration. This is the part that you might see. So here we have an example. Find the derivative of the integral from x to x squared arctangent of t over t to the 4th plus 1. All right. Well, How do we do that? Now, I'll tell you the way not to do that. The way not to do that is to say, how do I find the antiderivative of arctangent of t over t to the fourth plus 1? Let me think about that for a long time and make a wild guess and probably be wrong. So that's not the way to do it. What is the way to do it? Well, remember, tests should be fun. And this theorem is also fun, dimensional. So perhaps we should use the fundamental theorem. In fact, there's a nice fact you should know. We don't use it very often, but it's cute enough, we should write it down. It says the following. If I want to take, in general, the derivative from a function g of x to a function h of x, f of t dt, what would that be? It would be f of h of x times h prime of x minus, yes, f of g of x times g prime x. Right. And what you're doing here is this combines the fundamental theorem of calculus plus the chain rule, plus a little bit of the property that you can break things up into pieces. So really, this is a straightforward, do you know the fundamental theorem of calculus problem? And there's not much more to it beyond that. And so we can say then that the derivative of the integral from x to x squared of arctangent t over t to the fourth plus 1 dt is, all right, this will be a little bit long to write, but this inside part, this is my f of t. So the first thing is I'm going to take the x squared and I'm going to put it in everywhere I see t. So that's the plug in x squared into this expression. So I'm going to get arctangent of x squared over x squared to the fourth, which is x to the eighth, plus 1. That's the first term, f of x, f of h of x. What do I need to do next? Multiply by 2x because I need to get the h prime. So multiply by 2x minus. Now I come here. I'm going to now put in the x. So everywhere I see t, I put x. So that's arctangent of x over x to the fourth plus 1. And then what do I do? That's my f of g of x, and I do times g prime. G prime is 1. And so I just leave it like that, times 1. Okay, and now at this point, what can I do? Yes, right. Don't do anything else. Don't do anything else. Leave it like that. There's two reasons why. First off, you'll get full credit for it. That's a good reason why. Second off, this is not so much important to you, but it's easier for us to see what you're doing and to see what your logic is. So we can figure out what kind of mistake did you make if you made a mistake. Heaven forbid that would ever happen. But the other reason is, if you tried to keep going forward, odds are pretty good you'd make a mistake. Don't make mistakes. So if you don't need to make a new mistake, don't make a new mistake. Keep the mistakes you already have. That's good enough. All right. We've been going pretty quickly. All right, maybe we should catch our breath for a second. How's everyone doing? Swell? Okay. All right. We're getting close. We'll make it. We'll make it. Any questions on anything we've talked about so far, now that you see an empty screen? A blank slate. Okay. So, the next thing I want to talk about is substitution. So substitution, I should point out, and I didn't write it down here, but this really, think of it as connecting to the chain rule. So the chain rule was a really important rule when it came to taking derivatives, and substitution is probably the most important rule that we have for taking integration. The reason I say that is integration is really tricky. There's about 8 things that we can integrate, and only those 8 things, and nothing else. And with differentiation, it's like, oh, you give me anything, I can integrate. I can differentiate that, no problem. I can do that till the cows come home. But integration is hard. So the main tool that we have is to say, well, let's try to make it look like one of my 8 things. And so what we're doing here is we're trying to find a way to simplify it. In many respects, you could say what's happening with integration is it's repeatedly simplifying over and over again until what you have left is something simple enough that you can say, aha, this is one of my 8 things, I'm good to go. Now, how do you know what to substitute? There's one piece of advice here. I want to just point out that there's 2 ways to look for your substitution. So one way that we write the chain rule is as down here, integral from a to b of f of g of x, g prime of x dx equals the integral from g of a to g of b, f of u du. One way to do it is to say, well, let's look for my f of g of x. And in particular, let's look for a function in a function. And then that's oftentimes people say, okay, that's how I'm going to look for my substitution. What's my function on the inside? That works really well. It's not perfect, but it works really well. The other thing to do, and I'll go over this a little bit more on Sunday, is to look at the second part here, this g prime of x dx, and say, okay, maybe I have this little part here that hooks up to my dx. That's probably trying to hint at a substitution I should make. And so if I can pick up on what's my g prime of x dx, that can be hinting what's my substitution for you. And this will be more clear, as I said, as we go on. Okay, and then the last word of warning, make sure you account for all the occurrences when you make a substitution. So when I say all the occurrences, make sure you get your function, make sure you get your d, whatever your variable is, and make sure you get your bounds. Don't forget to update your bounds. And I will say, the people who grade this exam are going to be told to be very picky. If you change your variable and you do not change your bounds, you will lose points. Hopefully just 1 point, but possibly several. So keep updating, keep updating. All right, so let's do an example. So here we go. I want to find the integral of x times sine of x squared plus cosine of x squared, and that whole expression has been squared, times sine of x squared dx. What a weird, very messy and ugly expression. Thoughts? What can we do? What do you mean by separate? Well, I can't quite separate them yet because there's that square term in there. So what can I do if I want to separate them? That's not a bad idea. It's oftentimes a really good idea to start pulling things apart. Say, look, if I have an integral, let me pull them apart into the little pieces. Let me work on each piece individually. Right now I can't pull them apart because there's that square. What can I do with that? Yeah, I can square it. I can FOIL it. All right. So if we do that, this will become the integral of x times. Yeah, it's very subtle. That's my fault. Sine squared x squared plus 2 sine x squared cosine x squared plus cosine squared x squared. That's the part here, times sine of x squared dx. And you're probably thinking, you've made it worse. That's probably true, but sometimes you have to make it a little bit worse before it'll get a lot better. Sorry, what? Someone was saying sine squared plus cosine squared. Right, that equals 1. But what about the fact that there's an x squared on the inside? Is that going to mess that up? No. It doesn't matter. Sine squared of anything plus cosine squared of the same anything is 1. Doesn't matter what the anything is. Could be x, could be theta, could be x squared, could be a smiley face. Whatever it is, it becomes 1. Okay, so this is good. So this is the integral x 1 plus 2 sine x squared cosine x squared sine of x squared dx. Now somebody just a few minutes ago said, let's pull it apart. So let's actually do that now, because we can almost do that. Before we pull it apart, we will have to do a little bit, which is we'll have to multiply through. So I'm going to multiply the x in, and I'm going to also multiply the sine of x squared in. So then I'll have two things being added together, and I'm just going to go straight ahead and pull them apart separately. So the first term would give me x sine of x squared dx. The second one would be 2x sine squared of x squared cosine x squared dx. All right, we are making progress. These are now separate integrals. So I can do them independently of each other. What I do for one is independent of what I do for the other. So don't get too caught up on, what's something that works well for both. Focus them one at a time. Suppose you saw this, x sine of x squared dx. What's a good substitution to make? X squared is a fantastic substitution to make. And the thing that tells you x squared is a great substitution is it's a function on the inside. There's g of x, sine of x squared. The other thing that tells you it's a great substitution to make is if you think of it as x dx as being my g prime, well, if I wanted to get an x dx, I would probably start with an x squared. And so there's two hints. Okay, so here I'm going to make a substitution. U is equal to x squared, which tells me du is 2x dx. Or if you like, 1/2 du is x dx. So if I make this substitution, this becomes the integral of 1/2 sine of u du. So the 1/2 is coming from the x dx. Sine of x squared becomes sine of u. What is the, can we integrate this? Do we know what the antiderivative of sine is? We do know what the antiderivative of sine is. The antiderivative of sine is negative cosine. Yeah, we always try to catch a few people with that one. Okay, so negative 1/2 sine of u. Okay. All right. Oh, yes. Thank you. Whew. Thank goodness it's the last day. All right. Good. Okay. All right. We'll come back. Let's focus on this one for a second. And I'll switch to a different color for this one. Okay, now, what's a good substitution to make? Yeah, sine of x squared is a better substitution here. Now, if you say, do I have to get the best substitution on the first try? And the answer is no. You make a substitution. If it makes it simpler, that's good. Get it simple. And you say, oh, now I see another substitution I can make. That's okay. You can make a chain of substitutions. That's perfectly fine. As long as you keep making it simpler, you're okay. So u is equal to sine of x squared. What would du become? 2x cosine x squared dx. And check it out. I have a 2x cosine x squared dx. So that this integral with this substitution, which notice that it's a different substitution, becomes the integral of u squared du. Well, what's the integral of u squared du? One-third u cubed. Then there's a constant c. Okay, now it's time to finish this off and put things back together. So, from the first integral, we saw that when we made this substitution, u equals x squared, we got the minus 1/2 cosine u. So if I rewrite this in terms of x, the first one will be minus 1/2 cosine of x squared. That's the first one. From the second one, I'm going to get plus 1/3 u cubed. But what was u in the second one? Well, it's a slightly different one. Sine of x squared. So we get sine cubed of x squared. And then I have a single plus c. I don't need to have two plus c's. They combine together into one constant. Constants absorbs each other. Constants absorb other constants. Now, if you're thrown off by using u in two different ways, then you can use a different letter here. You could use v, or perhaps a w. But anyways, that's substitution. I will say you should know substitution, because almost on every single test there are lots of substitution problems. You should know that. You should know it. Okay. So let's talk applications. We know one application. I guess technically we know two. Averages and areas. So the way we started thinking about integration was thinking about area. So it's not unreasonable to say, well, we can use integration to find areas. So if I have f of x is greater than or equal to g of x between x equals to a and x equals b, then I can find the area between those two curves. I integrate from a to b, f of x minus g of x, where f of x is the top curve. G of x is the bottom curve. Okay, so in particular, I think of f of x minus g of x. That's my height. I'm integrating my height. Now, if there aren't any bounds given, so sometimes they say, well, find the area between these two curves, and then they say, but what are a and b? If they don't give you a and b, then that becomes part of the fun problem. And the way you find a and b is you say, well, where do they intersect? You set f of x equals g of x, and that will help you find when they intersect, and you solve, and the solutions will be a and b. It might be possible, or required, I should say, that you might need to do several pieces. This can happen, for instance, if your curves go and they intersect at multiple points. So you're changing what's the function on the top. It might be possible that you have a function like absolute value. When you have a function like absolute value, it requires that you work one piece at a time, a piecewise function. So if you need to break things up into parts, that's perfectly okay. There's nothing wrong with breaking your integral into several parts and working on each part. Related to area is the idea of average. If I want to find the average of a function between 2 points, so say my function is f of x, I'm going between x equals a and x equals b, then the average is 1 over b minus a, the integral from a to b f of x dx. So let's try an example. Let's find the average of the following function, x over x squared plus 1, where x goes between 0 and 2. Well, we're in luck, because we happen to know what the average is. There's a formula right over here. So the average is going to be 1 over 2 minus 0, a and b. So 2 minus 0, 0 to 2 of x over x squared plus 1. All right. Now, unfortunately, x over x squared plus 1 did not make our list of 8 things that we can integrate. So we're going to have to find a way to rewrite it, which surely means there's a substitution waiting to be made. I will also say that whenever you encounter a fraction like this, there's probably one of 3 things that occur, of which really there's only 2 that you should think about. What are the 2 things that you might see in terms of a fraction showing up? natural log, 1 over u to u, or arctangent. Okay, so you should automatically, if you see a fraction, you should say, I wonder if there's a log or an arctangent involved. Now, how can you tell which is which? Well, it's a log if when you take the derivative of the bottom, you get the top up to a constant. It's an arctangent if you say, well, I have a plus 1, and if I have my whatever it is squared, and I make that my substitution, then the derivative of that is somewhere on the top. Which case are we in? I'm being very vague when I say the arctangent. But which case are we in? We're in the log. One of the things that tells us we're probably not in the arctangent is if I wanted to make it look like arctangent, I need it to be u squared plus 1, which would mean my substitution would have to be x equals u, which doesn't do anything. It just changes the variable name, which doesn't change anything about the integration. So let's try x squared plus 1. So I'm thinking it's a log. So when I'm thinking log, I say let u equal the whole denominator. What would du be? 2x dx, and which is very convenient because we happen to have an x dx up here. Another way for us to say this is 1/2 du is x dx. So this will be 1/2 from here. Then I'm going to have an integral, and let's update the bounds. These were x bounds. So what I mean by that is this was x equals 0 to x equals 2. What are my u bounds? If x equals 0, u would be 1. U is x squared plus 1. If x equals 2, u is 5. All right. Now we're ready to go into here. The x dx will be 1/2 du. So I'm going to put another 1/2 out in front. And I have a du. X squared plus 1 is going to be u in the denominator. All right, so this is looking much more reasonable because this made our list of things we can integrate. The integral of du divided by u, ln of u. And as a farewell to our great SI person, I will put absolute values in there, even though you would not need to put them in this case. But she loves absolute values, so we'll put them in. From 1 to 5. We're almost done. So that's 1/4 natural log of 5 minus 1/4 natural log of 1. I know this is good enough, but I do want to say at least one thing we can do. Natural log of 1 is 0. We know at least that much. You know, show the graders like, I know about log. I know log. 1/4 log 5. And we're done. All right. And that brings us to the last slide, our very last slide of the semester. We've had hundreds of these, and this is the last one. Separable differential equations. These are very fun problems. What is a separable differential equation? Well, it's a differential equation, which means that there's a derivative involved. That's what the y prime tells us. Separable says I can separate the variables. So in particular, I'm going to have something in the form y prime is a function of x times a function of y. And I'm also going to have an initial condition. Every differential equation, if you're going to solve it, has an initial condition. So this says y of x naught equals y naught. So if I plug in my x value, I get my y value. Now the 3 steps are very straightforward. So don't get intimidated by any one step. Separate, which means isolate the variables. Put all the y's together. Put all your x's together. That's step 1. Step 2, integrate. Integrate each side, which is find the antiderivatives. You only need 1 plus c. Step 3, solve for c, and then solve for y. That's the process. So here we go, our last example. We're told that y prime is cosine of t over 2y plus 2, and that y of 0 is negative 2. We want to find y. Don't worry the fact that this says t, not x. We're not tied to variables. So this y prime you should think of as dy dt. So dy dt is y prime, is cosine t over 2y plus 2. So the first step is to separate. 2y plus 2 dy is cosine of t dt. All right, step 1 is done. Now we go to step 2. We're going to integrate both sides. What is the integral of 2y plus 2? Y squared plus 2y. What's the integral of cosine of t? It's sine. I saw the sine. And then we need the plus c. Okay, that's step 2. Now we're ready for step 3. This doesn't have a very snazzy name. I like the word uncomplicate just because it's such a silly name, it helps you remember. Separate, integrate, uncomplicate. But really, it's just finish it off. Okay, so to finish it, let's use our initial conditions. Y of 0 is negative 2, so I take negative 2 squared plus 2 times negative 2 would be sine of 0 plus c. 4 minus 4 is 0. Sine of 0 is 0. And so we can conclude that c is 0. So now we have y squared plus 2y is equal to sine of t. But I want to solve for y. There's not quite there yet. We're close. We're close. The problem is we have two y's involved. There's a y in the y squared. There's a y in that 2y. I want to get to single y. What's something I could try to do here? I could complete the square. Very conveniently, we've left a space here. So let's add 1 to both sides, because that would make y squared plus 2y plus 1 a perfect square. And the reason that that's useful is I can rewrite this as y plus 1 squared is sine of t plus 1. There's now just a single y, but I'm not quite done. I need to get y by itself. Okay, so I need to get rid of the square. How do I do it? Take the square root. So y plus 1 would be square root sine of t plus 1. Is that right? It's plus or minus. But I have to choose. It can't be both of them. Must I choose the plus or must I choose the minus? The last choice of the semester. Is it plus or is it minus? Oh, Renee is going with minus, but do we trust Renee? You should trust Renee. She's right. It's minus. Okay, good. Now, why is it minus? It's minus because we have this initial condition. If I chose plus, I cannot satisfy the initial condition. Negative 2 plus 1 would be negative 1. Square root of sine of 0 plus 1 would be positive 1. So the way I know what to choose is I go back to my initial condition. That will help me make my right decision. So whenever you have a choice, plus or minus, you get to come back and say, well, which one would actually make my initial condition work? And that's how we make the choice. And as someone said, we weren't done yet because we have to move the minus 1 across. And so therefore, our answer is minus 1 minus the square root of sine of t plus 1. Our final answer to our final problem on our final piece of paper, because this is our final lecture before the final. Thank you for coming. It's been a great semester. I hope to see some of you, maybe most of you, at the review session on Sunday. I really hope to see all of you next Thursday for the final. All right. Have a good day.